Hey, in this video we are going to look at how to tell, or what's going to happen anyway, when we have an acid that is strong versus an acid that's weak, and same thing for bases. Let's just review real quickly that if we have some acid, we can write the equation for the ionization this way as Bronsted-Lowry or as Arrhenius. We can also write it as a reversible reaction, so this is just the reverse of what was on the previous slide. And then we actually end up writing it this way with a double-headed arrow in between. So notice the double-headed arrow again shows that this is a reversible reaction. Okay, but as I warned at the end of part one, that does not mean that the two reactions in the reversible reaction are the same. They are probably not. All right, so here we go in part two. Now, if the forward reaction is dominant, and there's really no way for you to know that at this point, I'm just going to have to tell you that the forward reaction is dominant. If that's true, then all of the acid is ionized. Officially, we would say it's ionized. It's okay to say the word dissociated, I suppose. All of it is ionized or dissociated if the forward reaction is dominant. That means we get the largest possible amount of hydronium ion produced from that acid. And so we say, because it produces a lot of hydronium, that the acid is strong. Notice that strong simply means completely ionized. Strong means completely ionized. That's all it means. It's not about how much it burns. It's not about concentration. It is about whether or not it is completely ionized. Okay, so strong meaning completely ionized. Now, to kind of connect this to the Bronsted-Lowry model, if we have a really strong acid, the one that completely comes apart, then the conjugate base, the particle that's left when the hydrogen comes out, is very weak. Okay, now we haven't defined weak, but we can imagine, I think, that weak means not completely ionized or not ionized much at all. Okay, so here is an example. This is hydrogen chloride and water, which is going to form hydrochloric acid. Okay, so we've got hydrochloric acid here. I'm telling you that hydrochloric acid is a strong acid. You can't know that by looking. I'm telling you hydrochloric acid is a strong acid, which means that this HCl is going to completely come apart. All of it's going to come apart, and we're going to get lots of hydronium, and lots of chloride ion. And we will, for all intents and purposes, have no HCl left after we're done ionizing this. Okay? Now, if the reverse reaction is dominant, the one going from right to left, then most of the acid remains that's unionized or undissociated. That means we only get small amounts of hydronium, and we say the acid is weak. So again, if it's weak, then not completely ionized or partially ionized. Now, we talk about this like it's one thing or the other, strong or weak, but in reality, strong is completely ionized, but anything less than that is not necessarily weak. I mean, there's got to be some dividing line, and that dividing line will be kind of sliding. So we would certainly say 1% was weak if it was 1% ionized, or 2%, or 10%, but what if it was 50% ionized? You know, there's a little bit of gray area here. And again, if it's a weak acid, then the stronger the conjugate base. So remember, the conjugate base is what's left over when the hydrogen goes away from the acid. All right, so I have here, this is hypobromous acid, HBRO. Put it in water. This is a weak acid. Again, I'm just telling you that. That's the only way for you to know that. And so we do not get very much hydronium ion, and we do not get much of the hypobromite ion. We get a lot of this to start with. We end up with a lot of this. This reaction, the forward reaction, is not dominant. The reverse reaction is the dominant reaction here. Now, there is a way to know whether or not something is strong or weak, and that's what we're going to get to in the next video.